Okay, this video is the part of the previous video. So simply we were talking about the unit of the entropy, that is joule per Kelvin per mole. Why this has happened? Because the Kelvin is for the temperature and joule per mole is for the heat. So it is then important to determine that the entropy is an extrinsic property, and other than this to be determined is that it is a state function. So if we consider some things to be considered, like from entropy changing from the A to B, so we can write these equation or the entropy symbol. We can write the entropy symbol in the different form that is going to be appeared in the next page. So if we say when the reversible change is occurring from state A to B and back from B to A, so it follows this equation where the change AB ds plus BA ds is equal to 0. And now we have well explained or understand the quality or the effects of the entropy on the chemical rate equilibrium, and also the factors that are affecting to it, and also the nature of the entropy, it's extensive and it's the state function. So let's talk about the other physical significances. Entropy cannot be defined easily as like work, enthalpy, and energy, and not a simple precise interpretation is not easy. So however, for the discussion we should study the physical significance. So let's talk about the physical significance. Means that we will study the entropy in the concepts of the different views, in the concepts of the different theories. Let's talk and let's study about these factors. The first physical significance is the entropy is a measure of disorderness. If we have said this variously time that entropy is a measure of disorderness, where we are saying that this entropy is the chaos, this it is the disorderness, it is the randomness of the system. So we can understand this terminology with the help of the Gibbs free energy Gibbs theories, where it is said that it is actually the mixedness of the system. Therefore, as the system passes from more orderly state, what does that mean? When a system is changing from the more orderly state towards the less orderly state, means that the system is going to be less organized. A system is going to be from the organized or managed state into the messed up state, into the less organized state, or into the less orderly state. In this way the entropy of the system will increase, and we will say in as a subsequently means the fully meaning increase in the entropy simple. If the on the other hand the change is in such a way that a system is going to be arranged, our system is going to towards the highly organized way, or it is going towards the more orderly state from the less orderly state, it means that the increasement the decrease of the entropy will take place, because the system is going to decrease its disorderedness. So the entropy of the system will decrease if the system is moving from the highly entropy will decrease, means that from the less order stage towards the highly ordered stage the entropy will decrease. For example, when a solid changes to a liquid, a solid, you know that the particles are highly arranged. When the particles change the situation change the arrangement from solid in the bonding or solid arrangement into the liquid arrangement, means that they are going from the highly ordered state towards the less ordered state. So by this it means that the disorderness is increasing and the entropy is increasing. So when we say that this liquid state is not ending up, rather this liquid state has started to be converted into the gaseous form by evaporation, so it means that the more arranged molecules in the liquid will be highly disordered, or highly less orderly arranged, or highly disordered form of the molecule of the gas will appear. So we can say that the entropy of the gas is always higher than the entropy of the liquid, because the molecule of the gas are highly disordered as compared to liquid, and the entropy of the liquid is more higher than the solid, because in case of the liquid the molecules are relatively lesser organized. The entropy of a mixture of gases is greater than the sum of the entropies of the individual gases. What does that mean? The entropy of the mixing of the gases means that the gases are mixed up, means that before that the gases, one kind of the gas mean individual gas, we have specific type of the arrangement, has specific type of the polar lines, or some type of the some specific type of the like London dispersion forces and all other forces make them stabilize somehow. So but when we mix the gases, so their nature is different, their attraction repulsion towards each other is different. So in this way the randomness of the system increases. So we can say that the entropy is interpreted on the kinetic molecular theory in term of randomness, because we have get to know that the entropy is the randomness of the system. So the distribution of the atom and molecule in space and energy state is discussed, where we have said that the entropy of the gaseous state is more than the liquid, and liquid entropy is more than the solid. As you know, their arrangement of solid is highly organized, liquid is lesser, and gas is least arranged molecule. Thus the entropy of the universe tend to always increase, because most of the time the solids are getting converted into the liquid, like liquid are getting vaporized. So in this way we can say the universe entropy is increasing, as you have studied in the previous form, in the previous lecture, where we said that the entropy of the system is increasing because the randomness of the system is increasing. The chemical reaction is going towards the equilibrium state, and equilibrium state in itself is the proof of the highest state of the entropy that we will discuss next. Here we will study the entropy in different way. When the heat is supplied to the system, some part of the heat is used in the doing work. So this heat is called the available heat, because this heat is available for doing the work. And the remaining heat that is rejected or that is not used is called the unavailable heat. That is actually the Q2. So the second law of the thermodynamics says that entropy is a measure of unavailable heat, means that it measures the Q2. The process in a nature is generally spontaneous. We know that in the nature the most of the processes occurring by their own accord and are the spontaneous reactions. So spontaneous reactions are usually irreversible. In such process the entropy of the universe is continuously increasing. The unavailable energy goes on increasing and the workable energy goes on decreasing. A spontaneous process comes to the end of the equilibrium. It will come to an end of equilibrium, and as the equilibrium at the maximum at equilibrium, the entropy is always maximum. It means that whenever a reaction is occurring in the nature is mostly spontaneous, it's irreversible, and it will lead towards the equilibrium state, and equilibrium is a state where there is the maximum entropy. So means that the entropy of the system is always going to be increased. Entropy is a measure of the thermodynamic probability. Another physical factor to be determined is the entropy is a measure of thermodynamic probability. A natural or spontaneous process is always occur from less probable to a more probable state, means that it's lesser probability, or it is less probabilized to the water to be on the higher state. It will tend to move towards the lower state. So it means that the things are going to be from lower probability or chances towards the higher probability. So further determination of this factor is in this way. Okay, the state of equilibrium. The state of equilibrium is a state of maximum probability. Means that we have said it earlier that equilibrium is a state where the probability, where the randomness of the system is maximum. Any system when move left to right and then from left to right, and simply it reaches to the equilibrium state. So it is more probable state. Therefore, a direct relationship exists between entropy and thermodynamic probability. Taking this into consideration, Boltzmann put forward the following equation connecting entropy with the system of the thermodynamic probability, where the entropy is equal to K natural log W, where K is the Boltzmann constant, W is the thermodynamic probability, S is the entropy. So this system equation has become basis of the modern statistical thermodynamics. This equation is showing that the thermodynamic probability, what is the thermodynamic probability? Equilibrium. The equilibrium attaining capacity of a chemical reaction is directly related, entropy is directly related to the thermodynamic probability, which is the equilibrium state. The condition of maximum entropy is convenient criterion, means that when we want to understand the equilibrium, when it will reach, how it is reached, the point we can indicate or we can point out. So we will check, or we should find out the maximum entropy stage. Where the maximum entropy stage lies, there is the equilibrium stage. So if the equilibrium stage has not occurred, it means that in that non-isolated system we should predict the process that will continue to proceed on for the spontaneous process until the more positive randomness or entropy occur, and at the end the equilibrium stage is obtained. Let's talk about the difference between the state function and the path function that we have talked today a little. I want to make this concept to be clear in your minds. The state function are the properties of a system that depends only on its current situations, current state, and are independent of the path by which the system reached to that current state. But in the path functions are the properties of the system that depend upon the specific path or process by which the system changes from one state to another. It means state functions are the states that talk about the current situation, current state, that doesn't talk about the ways that a chemical reaction has proceeded, the path it has followed. But in the path function, it talks about the specific path to be followed or not, and how this current stage or state has occurred. So describe what are the example of the state function. Describe the current condition of the system, such as temperature. It describes the current condition, mean the present condition of the system, such as temperature, pressure, volume, internal energy, enthalpy, entropy, give free energy. All of these factors are the state functions. And what are the path functions? Describe the energy transfer or work done during a process. It does not tell about the one stage that is obtained and that is the ultimate stage. It talks about the paths, what are followed, and what are the energies to be released, what are energy to be gained, and how this process has occurred, such as the heat is actually the transfer of temperature. Now it is not a single situation, it's the flow. You have studied in the Carnot cycle that T1 was a high temperature reservoir, T2 was a low temperature reservoir, but the Q2 and Q1 were the heat transfer pathway, means that the Q is about the pathway and the work done by the system. Thank you.